Hola, bienvenidos a todos al primer coloquio de este semestre. Muchas gracias por venir. Hoy tenemos el placer de tener con nosotros a Eric Chen, que viene de la Escuela Polytechnique Fédérale de Lausanne, en Suiza, y nos va a hablar sobre ejemplos de S-dualidad y teoría de gauge 1. Eric me dijo que va a dar la plática en inglés, pero puede recibir preguntas en inglés o en español. ¿Okay? Bueno, pues muchas gracias por aceptar la invitación, Eric, y adelante.
Gracias a ustedes por venir. Pues sí, I think for mathematical things it's better for me to speak in English, so I explain myself well, but please feel free to ask me questions in Spanish if you feel more comfortable. Okay, so thank you all very much for having me here and for coming. And it's kind of funny because S-duality is by no means my expertise. It's just something that I learned from physicists. But I want to emphasize that today the goal is to show that only just knowing a little bit of physics and really bare minimum can help both organize and predict mathematical theorems. And is the writing big enough to see for everyone? A little bit bigger, okay. So here's the plan. In a very toy model of a 4D QQFT. In the second part, I will explain a little bit about what is S-duality, and more importantly, the concept of boundary conditions. And from the second part, I will write down two equations, which I will call equation 1 and equation 2. And in the third part, I will talk about examples of equation 1, which you will see later. And, or rather, just one example of equation 1. And if we have time, then I will talk about one example of equation 2. But the plan of the talk is pretty flexible, so feel free to interrupt me with any questions if you have them at any point. Okay. So let me start with section 1. Okay. So I won't be giving you a rigorous definition, but I'll give you the properties that we use. Okay. So a four-dimensional TQFT is supposed to assign algebraic objects to manifolds of dimension up to 4. And if I give you a 4 manifold X, so here the 4 means the dimension is 4, it doesn't mean I'm taking the 4th power. Let me give this theory a name, Z. Then Z evaluated on a 4 manifold should roughly be a number. So you can kind of think of it as a 4 manifold invariant. And if I give you a 3 manifold M, then the theory is supposed to give you something like a Hilbert space. Over the complex numbers. So if you're familiar with some quantum theory, then you can think of this as a Hilbert space of states. So my theory is 4-dimensional, something like 3 spatial and 1 time. And assigning to a 3 manifold, I have some Hilbert space of wave functions, if you prefer to think that way. But you don't have to. Okay. And well, how do these two structures interact? They interact in various ways, but most importantly to us is the following. If I write down here, can you see? Okay. So if I pick X and Y, two vectors inside this Hilbert space, then the fundamental thing I can ask it is what is their inner product, right? So I can compute product inside this Hilbert space, that we can relate it to a four-manifold structure, which is that it is the number attached to the four-manifold obtained by extending M by an interval. Okay? So here I will write restrict X and Y, and I'll explain what I mean in a second. So what I mean is that here, technically, the four manifolds I'm considering have to be closed, so they can't have boundary. Same with the three manifold, it shouldn't have boundary. But when I multiply M by an interval, obviously I get two boundaries, both look like M. And what I'm trying to say is that if you give me vectors inside the Hilbert space, I can effectively close up the boundaries using those labels. Okay. Are there any questions about that? Okay. So let me go one step further and say what happens to two manifolds. So I have a surface, then the theory should give me a category. Okay. And just like 3 interacts with 4, 2 can also interact with 3 in the exact same way. So I'll use the same notation, but they technically mean different things. Right, so if I take X and Y, now objects, inside this category, then the most fundamental thing I can ask now is what is the HOM between them. Right? So I can compute their HOM and this is a complex vector space. It can be expressed alternatively in terms of this three manifold with boundary. Okay. So again, here I have a three manifold with boundary, and I'm closing up the boundaries using labels given by elements. So it's completely analogous to the previous. And let me just say that there are way more axioms, and so on. Okay, so you can imagine what happens to a one manifold or even a point, or you can imagine what happens if my three manifold had different surfaces boundary, and you can write down a lot of axioms, which are fun to do, but I will just need these, so I will only present these. Are there any questions? Great. So as I tried to explain, you can get rid of boundaries of manifolds with boundaries by giving them labels. Right? So this kind of motivates the following auxiliary definition. A boundary theory Y for the 4D theory Z is, I'll just write down the two most essential things. Regarding three manifolds, Y of M should give a vector inside Z of M. Okay, so this allows me to close four manifolds with boundary M, more or less. And at the level of surfaces, and again, this allows me to close up three manifolds with boundary sigma. And by the way, so whenever I write M, it will always be a three manifold, and when I write sigma, it will always be a two manifold. So I will ignore the 4, 3, 2 from now on. Okay. And we're going to even restrict our attention further because we will only be considering two types of manifolds, one of dimension 3 and one of dimension 2 in this talk. Throughout this talk, we focus only on the following spaces. And well, I'll put spaces in quotes. You'll see in a second why. At the level of two manifolds, I will always take sigma to be a Riemann surface. Or alternatively, an algebraic curve, smooth and integral over C. Whichever perspective you prefer. So there should be no problems with that restriction. Still very interesting. But for dimension 3, I want to do something a little bit exotic at first glance. So my model 3 manifold will be C over FQ. So this is a smooth algebraic curve over the finite field FQ. Okay. So that might seem kind of weird at first, but let me explain quickly why, and as we go, I hope you will accept that it's a 3 manifold in some sense. There are many reasons why, but maybe the quickest one to say, and it's also convincing, is that there is a fiber sequence for this space. So I can take, sorry? A fiber sequence. So I can take my curve over FQ, and of course it maps to spec of FQ. And what is the geometric fiber of this map? Well, it's just my curve base changed to FQ bar. So if I have a curve over an algebraically closed field, I basically think of it as a Riemann surface. So I think of this as dimension 2, this is dimension 1, and this is dimension 3. And more or less, you can also, if you hate this example, you can think of the following example instead, which is you take a surface, and then you fiber it over a circle. So you can construct these out of mapping to array of surfaces, if you like. But so we see something different. Are there any questions about these?
You're thinking of spec of FQ as one-dimensional?
Exactly. That's right. Yeah. So these two roughly have the same Galois group, which justifies why it's like a circle. Yeah. Any other questions before I give you the two main examples of TQFTs that I will talk about today? So I'll give you two examples, both of which come from U of 1 gauge theory. And for some reason, in my notes, I started with theory B, and theory A will come second. So this one's called theory B. And to tell you what it is, let me introduce really quickly some notation. So for X, a space for which the fundamental group makes sense, I will write rep pi1x C star to mean the set of homomorphisms from the fundamental group to C star. Well, I'll take it up to isomorphism, but for C star, it doesn't really matter. So if your pi1 is finitely generated, then you can really write down equations for this, and this is an affine algebraic variety. So this is an affine algebraic variety. Great. Okay, so my theory is called B, and first I'll tell you what it does to 3 manifolds. So for a 3 manifold, I will take it to be the vector space of algebraic functions on this affine algebraic variety. Okay. So it's an algebraic variety, it makes sense which functions are algebraic, and I'll take that as a vector space. So far, so good. Here. And just to make the analogy very clear, what happens to surfaces is kind of the same thing. But here I have to give you a category, right? So I will take the category of derived coherent sheaves on this algebraic variety. Okay. Well, if you don't like derived, you can just take coherent sheaves and you won't really lose much intuition about this. Let me give a little bit more information about what happens in the model cases that we'll consider, right? So if M is an algebraic curve over FQ, then it will actually still make sense to take its fundamental group. And as Omar pointed out, the sequence here will look very similar to a fibered circle. Okay. So I start with this sequence. And this is a slight lie, but more or less, this group is Z. And more or less, this group is like Z to the 2 times the genus. Okay. So really, this representation variety is not so complicated. It's something like picking 2G plus 1 complex numbers. Not super complicated. And here it's even simpler because you can actually just take the topological fundamental group of this surface, and you see that it's isomorphic to C star to the 2G. Okay? Make a quick remark for some people who might prefer to think of this from a different perspective, is that if you have a line bundle, a complex line bundle with connection. So if you don't know what this is, you can think of the representation perspective. Line bundle with connection, then from this you can make a representation of pi 1. And this process is called taking the monodromy representation. Sorry, the connection has to be flat. Okay. So this perspective might make it seem more clear why theory B came from U of 1 gauge theory, because I'm more or less looking at complex line bundles with flat connection. But the 2 perspectives are equivalent. Yeah, so I can draw. So maybe here is a loop in the base. It's kind of like the fundamental group. And over it sits complex lines, right? So maybe here is my base point that I'm taking the fundamental group with. If I start with a vector, I can, the connection tells me which sections are flat, right? So I can go around, and when I come back, maybe I'll end up at a different place. Then this will be the action of gamma. Yeah. So it's like taking the kernel of nabla, of the connection. Okay. Are there any questions about theory B? Now I'll tell you about theory A. It somehow formally looks very similar. So just tell you what it does directly for the 3 manifolds that are our favorites. So for algebraic curves over a finite field.
Call it A.
Yeah, thanks. Yeah, so this will be A of our model 3 manifold. Here I functions, algebraic functions on something, right? So here I will take functions also, but continuous functions on pick of the algebraic curve. Okay. So C means continuous functions, and pick here, it's really just a set. So it's the set of isomorphic classes of line bundles on C. So if you've never thought about this before, it's actually quite concrete. So more or less, using the theory of divisors, you can think of the Picard group as just, I take a huge direct sum over all points of the curve of copies of Z, so that's huge. But then I will quotient out by the field of So a meromorphic function, we can take it and report its poles and zeros to get a tuple of integers indexed by points of the curve. And the Picard group is more or less a discrete group like this. So I'm just looking for functions on this group. Yeah. And one thing I'd like to point out right now is that the Picard was a set, but it's also a group under tensoring of line bundles, right? So Picard is a group and it acts on this. We have the structure of a representation by an abelian group. Okay. And now let me tell you what the theory does to Riemann surfaces. And again, it will look very similar to that, but one categorical level up. So it will be the derived category of constructible sheaves on Picard of the Riemann surface. So if you don't like to think about constructible sheaves, I'm basically talking about sheaves of complex vector spaces. So to distinguish it from coherent sheaves, which are algebraic functions. Okay, so here when I wrote pic, I really just meant the set. Here, when I write pic, I mean the moduli space of line bundles on sigma. So it's a space with respect to which I can consider sheaves. And just to give you a flavor of what this object looks like, it's actually quite simple as well. It's isomorphic to, well, it's connected identity component, which I'll write pic 0 sigma. And group is Z. So I have a bunch of components indexed by integers, and the identity component is what I call pic 0. This part parameterizes degree 0 line bundles. And this part parameterizes the degree. And furthermore, the structure of the identity component is very explicit. It's a complex torus of dimension G. Sometimes people also call it the Jacobian. Any questions about theory A? Okay. So I actually won't be using this category too much, so if you don't like it, it's okay. Just think of it as a categorical version of continuous functions. Okay.
Are there many theories?
Are there a lot of theories? Yeah. There are a ton. Yeah, so here I gave 2 examples based on the group GL1, more or less. But you can imagine if I introduce a group G, then theory A and B can be modified with respect to that data. Yeah. And even the examples I just said, they all fall under the category of, or not really category, but the theory that you would call gauge theory. But there are more other examples as well. Yeah. Yes, exactly, yeah. Okay, so now let me move to second section. which is a concept that, as mathematicians, it's so hard to understand. But suppose that physicists told us that two theories are equivalent. Two theories, A and B, are equivalent. You don't have to worry about where they got this equivalence from. It's just they told you, and you trust them. Then what does that mean? It automatically predicts a ton of theorems. For example, for every three-manifold M, it predicts an isomorphism of vector spaces. Right. And similarly, for every surface, it predicts an equivalence of categories. And well, the way I spelled it out, it seems completely like unexciting and uninteresting. But usually when we think of it from the mathematical perspective, these are possibly very unexpected. Okay. So this is the case for the two examples that I wrote down. I'll write example, but I'm just telling you it's the case, is that the theories A and B we have are exchanged by S-duality. In general, it exchanges gauge theory with gauge group G, with gauge theory with gauge group G check, which is the Langland's dual group. But for us, we're taking GL1, so both are GL1. But if this makes sense to you, then you can wonder about how to redefine these two examples to get more complicated dualities. Okay. So let me spell out, for example, what is this isomorphism of vector spaces? Yes.
So you mean in exchange, like the B-type theory for G with...
Exactly. And then there's a statement dual to what you said, right? Like A G check with BG. That's also the case. Yeah. Okay. So let me spell out this first line in an example using our two theories and our model three-manifold, which is algebraic curve over a field. And in this case, it's already a pretty fancy theorem, which you can call class field theory. So in our language, it says that if we take the three-manifold to be a finite or a curve over a finite field, then on the one hand, we consider continuous functions on Picard, right? And on the other hand, we consider algebraic functions on the character variety. And they are isomorphic as vector spaces. So this is one very obscure way to say class field theory. In fact, we know a little bit more. We know that, remember, this is a representation by an abelian group. So it makes sense to ask what are its eigenfunctions. And if I take an eigenfunction on the left-hand side, it turns out that this corresponds to a delta function at some point. So I'll just call it delta chi. So Does it make sense why this is an example of this? Great.
I don't know how to make sense of the delta function. These are, what, algebraic functions on the character variety?
Yeah. So I was hoping no one would ask about why the delta function is algebraic.
Yeah.
But so there's a sheaf, which is a skyscraper sheaf.
Okay.
And this is like the function associated to that sheaf. So I also consider it algebraic.
Okay.
Yeah,
okay.
thanks. Yeah. Okay. And well, now let me give you an example of this equivalence of categories, which is basically a categorical version of that. So here's a theorem.
And does this also give you something like an action of the Picard group on the right-hand side? Because we had the action on the left and we didn't have it on the right.
Yeah, it gives you like a transport of structure. Okay. Yeah, but usually, at least from my like arithmetic perspective, I care about this one, and the points here are indexing the frequencies on the left side. So I don't usually think about Picard acting on here. I just think about it acting on here, and this is responsible for its eigen decomposition. Yeah.
So you think of this as something like the Fourier transform?
It's something like a Fourier transform. Yeah, and points here become the Fourier modes. Exactly, yeah. So all of that can be framed categorically, which I won't explain too much in detail, but let me just say that it exists. And you can call it geometric class field theory. Which says that if sigma is a Riemann surface, then the category associated by A and B will be equivalent. So on the one hand, we have constructible sheaves on the Picard. And on the other hand, we have something like coherent sheaves on the character variety. And just like here, there's kind of a Fourier decomposition happening. You can define what it means for a sheaf to be an eigensheaf. Basically a pure Fourier mode, and these will correspond to skyscraper sheaves. So far, so good. So already just by, if you read somewhere that, these two theories are equivalent, it predicts a bunch of theorems. But let me go a little bit further and consider boundary conditions. So suppose that they told us that these two theories, A and B, admit boundary theories, and that they are also equivalent. X and Y respectively. So X is a boundary theory for A, and Y is a boundary theory for B. Then what that means at the three-manifold level is that my isomorphism of vector spaces is not completely arbitrary because it has to preserve two vectors. Okay. And similarly at the categorical level, my equivalence of categories is not completely arbitrary because it has to preserve two objects. So whatever, well, at least in our context, when physicists find an equivalent pair of boundary theories, they might call this S-duality of boundary conditions. And the main goal of this talk is to convince you that if you read these sentences in physics, if you find someone say, I have an equivalent pair of boundary conditions, it predicts a lot of theorems for you to prove. So here, I'm sure there are more ways, but this is the most, I think, straightforward way to produce theorems from this. So we can, to make theorems out of it. We can take, for example, a three-manifold level. We take two other vectors that we like, which correspond to each other. So I'll call it XA inside A of n, which under the isomorphism of vector spaces, I'll call it XB. So this is some other pair of vectors that I know about. And I have a dual pair of boundary conditions. Then I can write down the following equation, which is equation. I can compute the L2 pairing. And physics will predict that it's an equality of numbers. Similarly, equation 2 will say that if I take objects, XA, inside A of a surface, which for some reason I know are matched with another object, XB, then the vector spaces obtained by pairwise Hom will be isomorphic. So these are the equations 1 and 2 that I mentioned in the breakdown of the talk. And I will for sure get to here to give you an example. And if we have time, we'll get to here. But just to say a few words, if you're interested, there are a lot of mathematical theorems of this form. And just to mention a couple, in equation A, I can put here things like automorphic periods, which is actually how I got into this business to begin with. And this is the theory of taking things like modular forms and integrating them over cycles and asking what you get. And yeah, so it's a very arithmetic subject. Another thing that could be considered in this, as an example of this equation, is enumerative mirror symmetry. So things like counting curves can be expressed by period integrals. They're both of this type. Although it's not coming from gauge theory, so you won't see it from the examples I wrote here. And for equation 2, some notable examples are, so we have a seminar these days on knot homology, which we've seen that has kind of two different flavors of calculation, and it comes from an isomorphism of vector spaces like this. Another example, which I will talk about if I have enough time, is mirror branes on Hitchin moduli. So this is another host of examples of equation 2. Check the time very quickly, and let me ask, are there any questions at this point? Okay. So this is great if you have a pair of theories that are equivalent, which we do. I just told you these are equivalent. Now we need S-dual boundary conditions to make theorems, right? And unfortunately, it's also difficult for physicists to find S-dual boundary conditions. And I think when they say it's hard, it means it's really hard because they guess faster. But I will keep those so you have, yeah, where is he? But at least in the context of gauge theory, there are some hints as to where to find boundary conditions. So in some sense, defining boundary conditions for B are not so difficult, but whether you find dual ones is luck. Yeah. So here's an example based on our two theories, and I should attribute it to Kapust and Witten and Gayoto-Witten. Basically, their motto was that you can look for boundary conditions, for boundary theories, from actions of the gauge group. So for us, the group was GL1, and let me take probably the simplest action we can think of, which is C star acting on C by scaling. And so I will not be telling you, given this data, how to make boundary condition for A and B, like the formula, but I will tell you the answer. And I will give some justification for roughly why that is the answer. Okay. So let's first look at what happens to three manifolds. Then my boundary theory, which I will call X, evaluated on this three manifold, B is a function on pick, right? Because it's a vector inside here. The function. What is the function? Following, I take a line bundle L and I evaluate it, and the answer is I count the number of global sections. So Q is the size of the number field. So Q to the dimension of sections is just the number of sections. So roughly what's going on is that I have a C star bundle, which I replace the fibers by C, which is the justification for why I came from this action. And well, this function is notoriously difficult, right? In the range where Riemann Roch is good, we can understand it, but otherwise it has erratic behavior. So this is more like counting sections. And now let me tell you the boundary theory that we have for B applied to a three manifold. So now the boundary theory for B, I'll call it Y. Well, this is a function on representations of pi 1 because it's a vector in here. Now I'll write you a formula which looks evaluated at a representation in rho. Then what happens is that I will take the trace of Frobenius on something. So remember, the pi 1 of this mapped to a pi 1 of FQ. This is the Frobenius I'm taking. If you were thinking about fibering over a circle the whole time, then this is the monodromy along the base circle. Okay? I'll take the trace of that on something, and it's the symmetric algebra. Let me write it this way. It's the exterior algebra on H1 of that representation. Let me make it more clear. So in terms of the fibering over the circle picture, I'm basically looking at a fiber surface, taking cohomology of that local system, and well, there's a monodromy left over from the base circle, and I take the trace. And well, I put an exterior algebra there, just because. So this but let me just say that you can interpret it. So using Lefschetz's fixed point, right? So this is a formula from topology that says you can count fixed points of a map, a self-map of a manifold, by taking some trace. Okay? So using a formula like this, you can interpret this formula as counting flat sections. So really, it's not so different from the previous. It's counting sessions, but now I'm counting only the flat ones. And yeah, I think I will leave you to imagine what happens to surfaces. You already know what the categories are, you know what it does to three manifolds, so maybe you can guess what happens to surfaces. Okay, so I think I will not get to equation 2, but I will definitely get to equation 1, which is more interesting anyway, I think. Okay, so let me just set you up again with what we're trying to do. We have two dual theories, A and B, which are written here. And then I have two boundary theories, which I'm telling you are dual, or rather some physicists told me are dual. And now I'm telling you that they told me that they're dual. And I just told you that whenever you have that set up, you have basically tautological equations that come out of it by taking L2 pairings. So now we're going to apply that to our theory of three manifold. That's basically equation 1 written here. So let's take I inside this vector space, a character of the Picard group. Well, I told you that it corresponds to a delta function at a point, but points on this variety index representations, right? So let me just give it a name. So call the point supporting delta chi, rho chi. So it looks more like a representation. So this is what I'm doing here is basically this step. I'm taking vectors that I know correspond in the two theories. And now I'll pair with boundary conditions. From that, I get a theorem. And it's one of the main theorems of Tate's thesis. So it says that if I take the integral over Picard of C of my character chi with my boundary condition, so I'll just write out the definition. Then recall that this function by itself was impossible to compute explicitly, but here I've taken a Fourier coefficient of it, more or less. And we can give an exact answer to that. So it turns out that this is the L function associated to rho chi. And if you've never seen this object before, I will write down a formula in a second, but it's some generalization of the Riemann zeta. Very mild generalization. And somehow the proof if you're coming from a physical perspective, is that it's done because we interpret both sides as inner products. So the physical proof of this is just that the equation is just, I take chi, I pair it with x of c, and it will be equal to delta chi paired with y of c. So this is manifestly the left-hand side. I took an L2 product. And here I took an L2 product with a delta function, which means I evaluated, right? So this is y of c evaluated at rho chi. And well, it's some work, but it's completely elementary to show. Starting from the formula I wrote down here, you can actually express it as a product over points of the curve of the quantity 1 minus rho chi applied to Frobenius at that point, Q inverse. So I just wrote down this formula so you see it looks like the Riemann zeta. But well, this is the physical proof, but then as mathematicians you can go ahead and try to prove this directly from a mathematical perspective. But knowing that it's true makes you more confident that you will be able to prove it one day. Okay, so I think I'll stop here, and thank you very much.
¿Hay preguntas para Eric?
To show that all these equations hold, but like, is there a proof that the two theories are equivalent, like a mathematical proof?
Usually there isn't, because the theories themselves don't have definition. That's the thing. So when physicists propose a theory, usually they're saying that there are aspects of it I understand, but from a mathematical perspective, it's not enough to axiomatize what exactly they mean. But that's kind of okay, because we can still prove theorems. Yeah.
So we just take the intuition of physicists to try and do our math. We take the physical intuition, well, their physical, well, not
yeah,
mine,
yeah, exactly.
Yeah.
And then you try to get math out of it. Yeah. But the short answer is no. Usually a theory doesn't have a definition, so you can't prove their equivalent.
And so is it true that the examples of theorems that you gave us today, they were all like, they were not guessed this way, they were all proven before this, but there are probably also already examples of theorems that came about this way, like the physics predicts this and now I'll prove it, right? But
that's right.
I just wanted to check, all of these were like
these
prior
were
to
all,
S-duality.
Yeah, these are all priorly proven theorems. But if I had time to get to equation 2, then there would be an example. Yeah. I think there was a question in the back.
Just a comment about your last comment, or a question about your last comment. You said that theorem is not, or I understood that theorem is not proved.
This one.
Yes, you gave the physics proof, but then what was your last comment? Could you comment on it?
So the last comment is that the thing I wrote called proof is not a mathematical proof. But knowing, kind of believing that it's true will maybe help you prove it. Although I didn't tell you at all how to actually prove this theorem. It's not so difficult, but I didn't tell you. These are not the ingredients to prove it. These are the ingredients to guess it. It's just a guess, yeah. Yeah. There is a math proof in his thesis, yeah.
Yeah, so you mentioned for the case of three manifolds that you had some equivalences with mirror symmetry, but those are three manifolds, so what's the version of mirror symmetry that you are mentioning there? I mean, do you cook up some symplectic manifold and some algebraic variety associated to those, or what was that comment? Could you explain a little bit?
So
You erased it, I think it's behind.
It was probably here with red color, right? So the reason I couldn't explain that well is because the examples I gave you are examples of gauge theories, which means that in the physical theory, you care about G bundles and sections of various associated bundles. But the theories that underlie, maybe you're thinking of homological mirror symmetry or enumerative mirror symmetry, then for those, first of all, it's not a 4D theory, so it's a different setup, it's 2D. And the underlying theory is not of gauge theory, it's what people call sigma models. So for me to explain exactly why it looks, why you cover that will be impossible because I'm also not an expert. But at least that's why I can't explain it very well right now.
And maybe two basic questions, just maybe more to do with the notation. When you're taking in this integral, but below Tate's thesis, you're taking the measure with respect to line bundle L.
Yes.
What does that actually mean?
Yeah, so...
Does Picard see that, I mean, you defined it over there, but what measure are you thinking of?
Let me give you two answers. Well, do you prefer Adels or do you prefer categories?
Categories, I guess, yeah.
Categories, okay. So you can take the Picard groupoid instead of the set, and then you take the groupoid measure. So every element is counted with the size of its automorphism inverse. Then it's that measure.
Thanks, yeah, then that makes sense, yeah.
Okay, yeah.
And then for the, when you talk about flat sections using this Lefschetz fixed point formula, with respect to what structure or connection are you thinking that those are flat? I mean, just...
Yeah, so if you're working in the arithmetic setting like I am here, there's no literal connection, right? But if the curve were actually a Riemann surface, then you can convert the representation of pi1 into a flat connection, and then you're counting flat sections with respect to the connection. Yeah.
Thank you.
Mm-hmm. Thanks.
I guess I have one last question. So in the formal definition I've seen of a TQFT, you couldn't actually plug in an algebraic curve over FQ. You needed like an actual three manifold.
Yes.
Is that part of this problem that you said that like these TQFTs don't actually have a formal definition?
Yeah, I would say it's part of the problem, but it's also a feature that you can plug in arithmetic manifolds, which are starting to predict things from number three.
Yeah. Okay.
So I think we're quite far from defining what it means to plug in arithmetic manifolds, but at least we have guesses as to what comes out. Yeah.
¿Alguna otra pregunta?
So maybe coming more from a geometry and topology of three manifold side, in here you're kind of giving an example where you have a surface bundle over S1. Are there any examples or work done on like hyperbolic manifolds or other kinds of, I don't know, geometric structures on 3D?
One thing I can say is there's work of my academic sister where she takes a symplectic local system on a three manifold, which is a circle. I think it has fiber over a circle. And she interprets some of what these invariants mean in terms of things like spinor norms and liftability of structure group and things like this. So there's some, but I don't think there are a lot.
Démosle las gracias a Eric de nuevo.